time factor changed the way that time was used. In one case, it was calculated just simple multiplication. In another case, there was a squaring of the time value. And it also changed the way that the other variables, like the measured y velocity and the measured y position and so forth, were being used to calculate the estimated current y position. So the factors are interacting. The key point here, they are interacting in a way that differs. There have to be at least two domains, otherwise there's no point in doing domain analysis. If the interaction is the same throughout the entire equation, then this is not something that you need to use domain analysis for. But when the calculation changes based on, as I said, one or more of the factors, then the domain analysis will allow you to pick values to be used that will allow you to test the calculations, different calculations, have confidence in the different calculations, but at the same time not test the combinatorial explosion that would be associated with trying to test boundary values across a number of factors. So what we're going to do is we're going to analyze the domain. Graphically is usually a good way to do it. There is also a way to do it with decision tables that I'm not going to get into here. If you're curious about it, you see that in pragmatic software testing, but that it'd definitely be way too dry and take way too long. But what you're going to do is you're going to do your analysis again, either graphically or with a decision table, and you're going to cover at least the on and off values. You are allowed to reuse values, off values, on values, so forth. That reuse is possible. You typically should cover the in and the out values. It'd be a very good idea if the in values exist and the out values exist. Reuse of the in and out values is possible. You use an in value for one domain as an out value for another, and that's perfectly fine. And then if the domain, if the rules change within a domain, and basically you get a subdomain like we saw with the frequent flyer example, then you should have additional potentially on, off, in, and out values associated with those subdomains. At the very least, make sure that you've at least got one test value in each of the domains that was created to avoid a situation where you've got an untested calculation. Different domains can be based on inputs, they can be based on outputs, they can be based on internal data sets. So just, whenever you see a lot of variables coming together to make up a calculation, then and you see that the calculation differs based on one or more of the variables value used for it, like you would get with, say, tax brackets or something, then this is a good spot to consider domain analysis. Domain analysis typically would include real numbers or integers. It can also include dates, can include sets and other kinds of data types. Usually when you're looking at something, if the values are more continuous, if you will, they can take on a longer range, the real number, an integer, date, time, so forth, then domain analysis is a good choice. If you're looking at something that's more discrete, if you will, where factors are true or false, or the factors take on a limited number of values, 3 or 4 values, say, then about a decision table is more appropriate. Okay. Now let me show you an example of this. Again, this is something that you can get more detail on in pragmatic software testing. I just want to give you kind of a taste of this thing. I'm not going to get into this in depth. This is a decision table that's defined, and it looks at, and those of you who took the listen to the decision table presentation, you'll remember this one, that we have a decision table that calculates a fine for someone who's been pulled over by the police. So we've got 4 independent conditions here, whether the license is okay, there's a warrant for their arrest, the registration is okay, the vehicle is okay. These are non-exclusive rules. You should remember that from the decision table discussion before. If the person is going to be, if the person has an invalid license, then they'll be arrested. They get a $250 fine for driving without a valid license. If the person has a warrant out for their arrest, they will be arrested. And again, they get a $250 fine. Rule 3 says if the person's registration is not okay, then give them a $25 fix-it ticket. Rule 4 says if there's something wrong with the vehicle, then give them a $25 fix-it ticket also. And then we have calculation of the fine based on excess speed here in rules 5, 6, 7, and 8. Excess speeds from 1 to 10, you give them a warning. If it's 11 to 20 miles an hour over, you give them a $75 fine. Rule 7 says if it's 21 to 25 miles an hour over, then give them a $150 fine. And if they're greater than 25 miles an hour over the speed limit, that's reckless driving, so they get arrested and they get a $250 fine. Okay, so that's a fairly simple decision table, and just coverage of the decision table alone would say, well, we have to have eight tests at least, and if we add boundary values to that, then we'd say 4, 6, 8, 10, 12, two values each for 5, 6, 7, and 8. But you say, well, what if I want to test the calculation here, and going back to the previous slide, right? If I say I want to test all the different possible combinations of the way that those things can work, and thus all of the different possible fine calculation options, the boundary value analysis, and combining all of those, you're going to get 208 tests. So that's not so good. So what we can do is use domain analysis. You say that the actions are the different domains, and you test one violator in each domain and one just outside each domain. This slide shows there's 208 different possible tests, which is hardly something we'd be interested in doing. And then if we say we're going to say, all right, we want to look at the 7 classes of speeds shown here, less than 0, that's an invalid, 1 to 10, 11 to 20, 21 to 25, 26 to max, and then greater than max. Tickets, none, warrant, fix-it, speed, and arrest, and then the arrest condition is either do or don't. We'd say we're not going to worry about the different inputs and output interactions, the boundaries. Then what we can do is we'll pick the biggest variable or factor, do the domain analysis on it, populate the condition that is needed to cover the different ons and offs. The next biggest, do the same, and repeat until we're done. So in that case, we can cover the domains here. Instead of 208 tests, it's down to 11 tests, which is less even than you'd say if you were testing the different boundary values with the decision tables. So the domain analysis can be applied in these decision table things in situations. Again, I don't want to get into a detailed explanation of how this works, but sort of whet your appetite a little bit if you're curious about this and want to try it yourself. Okay, so what we've gone through here, application of domain analysis to complex logic. Well, we started off with something pretty simple, the frequent flyer. Moved on to something a little more complicated, which is the aerospace example. Then we made the frequent flyer more complicated by having the rules change, and then we looked at what could be a fairly complicated situation with 208 combinations, and got that down to 11 tests that tested the different domains across the different analyses that were shown. So previously we've looked at things like decision tables, state-based methods, use cases, and pairwise testing. And in this webinar, what we've done is then looked at the testing that's based specifically on calculations that are being performed. So anytime you see a calculation being performed, good idea to say, maybe I can apply domain analysis here. These 5 techniques, from a black box point of view, are advanced techniques